over this break, the goal is to have you to be able to work through the majority of Chapter 10 and to be able to do this assignment that you can find on the internet. And I'll make a link for that, but it'll be these 9 or 10 problems. Let's see here. Yeah, it's just 8 of them, but they're fairly complicated, but they'll be fine as long as we just teach you about Chapter 10 and gases. So we'll just go ahead and work through that now. So just to get this up front and out of the way, Chapter 10 is pretty much all about one mathematical equation and the application of this equation that we call PIV-NERT. PIV-NERT is short for PV equals nRT. And it's the ideal gas law as well. And it relates pressure and volume to the amount of moles of something present to this constant of R times the temperature. And then we have those units of pressure as ATM, torr, or millimeters of mercury. Now, it's drawn on my screen with my finger, so it might not be the best, but these are pretty much the same things, and you'll see that throughout the notes. And then temperature is Celsius or Kelvin, but we're always going to make sure for us it's in Kelvin. And then volume's pretty much 99% of the time in liters. Some characteristics of gases. Unlike liquids and solids, gases expand to fill their containers. That's a very different concept than the other two. They are highly compressible and have extremely low densities. Gases are the only type of matter that is compressible. We can't squeeze water, not water. We can't squeeze liquids or solids, only gases. And that's because they're the only ones that really do have room in between their atoms or molecules, and that's the same reason they have low density, is because if you have a balloon, there's really not that much stuff in the balloon. So if you try to compress it, these can be made to get closer, and the pressure will go up, and we'll learn the math behind that. But their density, the amount of matter is so compressible, their density and their pressures go up. But in liquids and solids, everything is stuck together, so they are not compressible. All right, and then, as always, even on this computer, I'm doing this on my laptop, it didn't convert very well, but pressure is defined as the amount of force applied to a specific area. And then we will deal with atmospheric pressure a ton, because the unit we're going to talk about is ATM. And ATM is the atmospheric pressure. It's the weight of air over the divided by area. In pretty much all of our labs that we will do and activities, we will be at 1 ATM because we just assume we have 1 atmosphere of the air above us pushing down. So that is pretty simple. All right, the units of pressure, there's 2 that are old, and they are pascals and bar. And you'll use this one in physics, if I remember, a lot more. We never use pascals in chemistry. We have a bar, and that relates to a pascal. Let's see if there's, oh, that's the wrong thing. Nothing lower, so they must be on the next slide. We use these more often, and that's millimeters of mercury or torr. And once again, millimeters of mercury or torr are pretty much the same thing. And what that means that these units are literally the difference in the heights measured in millimeters of 2 connected columns of mercury. So it's kind of a stranger thing, no pun intended if you like those movies, but what will happen is the atmospheric pressure pushes on this amount of mercury, and then this tube was sealed with mercury in it and has a vacuum. The harder the pressure pushes down, the greater this mercury moves up. And so when we say we have a high pressure, that actually means we have a lot of air pressure pushing down, which is pushing the mercury up. A low pressure means that the pressure is not as much forced down, and so the mercury comes down as well. All right, so you need to know what millimeters of mercury are and what torr is. Torr is just the short way of saying millimeters of mercury, and you absolutely have to know this conversion. That 1 atmospheric pressure of air above us is equal to 760 torr, all right, or 760 millimeters of mercury. Now, when you watch the news, it will usually give you the pressure in inches of mercury, and that's just because we're Americans, so we don't deal in centimeters. And it never really does give you ATM. But math-wise, we will use ATM most often. All right, this is a manometer. I'm going to leave that for your reading. All right, so standard pressure or normal atmospheric pressure at sea level is equal to 1 ATM or 760 torr or 101.325 kilopascals. We really don't use this unit in chemistry, so don't worry about that. Just worry about these conversions, 760 to 1. All right, Boyle's law. You don't have to know each one of these, you just kind of got to be able to picture it in your head. Boyle's law says the volume of a fixed quantity of gas at constant temperature is inversely proportional to its pressure. So if I drew a picture of a graph, if it's inversely proportional, as one gets bigger, one thing gets smaller. So we're going to say that we have this inverse relationship. And we can all picture that. If we squeeze a balloon, the volume it occupies goes down. We're going to put these graphs together, and I don't know, I haven't looked at these notes in a while. Well, there they are. We'll come back. All right, we'll come back. So as P of V are inversely proportional, a plot would do this. I don't know if we need this. You can read this. I'm not going to worry about it. You can read it, but we don't need this math, and it's a tiny bit confusing. All right, so let's move from Boyle's to now Charles' law. And that says the volume of a fixed amount of gas at constant pressure is directly proportional to its absolute temperature. So what this is saying is the hotter the gas, the more room it needs. So this is directly proportional. So our graph would look something like that. Whereas temperature goes up, so does the volume. Avogadro's law. Avogadro has Avogadro's number, if you recall. And that was the amount of atoms or things in 1 mole. So Avogadro's law says the volume of a gas at constant temperature and pressure is directly proportional to the number of moles. Meaning that if we had a graph, if we have more stuff, then the volume will increase. All right. Now, that's not too hard to remember or to make sense. Let's go back to this slide I had a little while ago. I went right past it. It had this graph. Let me shrink it all. Up what I just barely had talked through, and that's all three of the laws. We'll just start at the top, and that's the blue line, and Boyle's law. As pressure increases, the volume decreases. So you will notice a decreasing slope in the blue line. And then the red law, that's Charles' law, says as temperature increases, the volume also increases. So that's directly. And then we had Avogadro's law in green that says as moles increase, the volume increases. Now, what we're going to do with this is turn this into a mathematical equation, which you can kind of already see at the bottom. But I'm going to move this over here, get rid of that. My computer's really bogging down, so we'll see if this works out. So what we're going to do, we're going to have a relationship where we say volume Then we're going to make a fraction out of it. And anything here that's pointing up means it's directly related or on top of a fraction. So our volume is directly related to the temperature of the gas, and it's directly related to the moles of the gas. And we use, this is a multiplication sign, we use N to represent number of moles. So that's the variable that will be N. Now, this arrow points down, which means it would be underneath this numerator, so it would be the denominator, so we'll put pressure down here. So just based on these three laws, we can come up with this relationship that our volume is, and I'm going to say roughly equal to, because these just say that they are related. It doesn't say they're equal to. So we're going to say the volume is related to the temperature times the amount of moles divided by the pressure. It's a very simple idea, and hopefully if you didn't get the first, go back and read this section on Boyle's, Charles, and Avogadro's law, and I think it will make great sense to you. Things get smaller if you push them. Things get bigger if you heat them. Things get bigger if there's more of them. All right, it's not complicated, and we can come up with a very clean mathematical relationship. Now, the only problem with this is this little squiggly isn't perfect. It means they're related to. So in order to get this to work, we throw in what we call a fudge factor. A fudge factor in science, and it's not something you would define, but it's something that we put in to make all the numbers talk to each other. In the gas law, this fudge factor, I'll put it in red, is what we call R. R is the gas constant that makes T, N, and P talk to each other. And if we have R there, then we can turn this back into an equal sign, where we can say our volume is equal to our temperature times our moles times this constant that makes things talk to each other divided by the pressure. Now this is usually written with P over here. And our PV is now equal to, we call it nRT. I have it written backwards, but that doesn't matter. PV equals nRT. That is Pivnern. Our pressure times our volume is directly related to the number of moles in something times this constant that makes these four things talk to each other times their temperature. This is Pivnern, and it is the equation that will govern everything. It's like the one equation to rule them all. So let's look at the problems we can now do if we have PV equals nRT. Basic Pivnern problem. It asks for pressure. So if we know that PV equals nRT, sorry, this is ugly. It's the top of a wobbly laptop screen. Then if we're asking for pressure, it must be equal to nRT over P. We just took P under, or sorry, that should be V because we're solving for pressure. And that leaves P all by itself. So P equals nRT over V. So now we just have to plug in. We have to find N, which is the number of moles. Now I gave you grams, and most problems will, so you have to convert grams to moles first. So you will take 20 grams and divide it by the molar mass of CH4, which is 12 plus 4 more, which is 16. And that is 1 1/5, which is equal to 1.2. And that will be N. All right? So then R, I didn't tell you, I should have. R is 0.0821. That's a constant. Now that constant has many different values depending on the units that we use, because there's different conversions for each type of different units. But we will most all the time use 0.0821 because we're going to use ATM and we're going to use Kelvin. All right, now our temperature This has to be converted to Kelvin. So it's 273 plus 30, which is 303. And then we divide that by the volume, which it told you right there, kind of hidden. This is pretty hideous, but that's okay. We're going to take all this and divide it by 4. And we plug that into our calculators, and we'll get an answer. Now, I have the answer, and it's going to look terrible here for a minute, but I'm going to delete all this. No, I'm not. I can't. All right, I'm going to move this, and we're just going to see what happens here. Okay, that looks really, really bad. But if you can look at the bottom, we have the 20/16, we have the 0.0821, we have the 303, and we have the 4, and we should get 708. Hopefully you were able to, or sorry, 7.8. Hopefully you were able to do that. Now there's 3 or 4 questions coming up in this that you need to do and submit those for grading.